We expand our discussion of simple harmonic motion into that of waves. Now, a wave, we defined earlier, but as a reminder, is a disturbance that propagates from the place it was created. So examples of waves are water waves, sound waves. There are mechanical waves. Imagine a slinky stretched out. You can shake it back and forth and send that disturbance down the length of the slinky. Now, waves transport energy. There's oscillations involved, but waves move through medium. The medium itself oscillates but doesn't move with the wave. Now, a way of thinking about that is my vocal cords right now are vibrating. If you were in the classroom with me, I'll pretend you are, you'd be sitting out in the classroom and your eardrums and the hairs in your ear would vibrate and you hear what I'm saying. The air near my vocal cords that I am exhaling as I speak isn't entering your ear. Because I have a classroom, let's say, of all of you in here, I believe it's 13 people or 16 people enrolled right now while I'm making this message. That can increase for my first lecture. But however many people are enrolled in the class, all of you aren't getting hit by the air from my vocal cords. That's not entering your eardrum. The disturbance is. So the air near my vocal cords is being knocked back and forth as my vocal cords vibrate. Those things that are being knocked back and forth, they're knocking their neighbors back and forth, and they're knocking their neighbors back and forth, and that propagates outward until that disturbance enters your ear. Another wonderful example is water waves. If you've ever been at a wave pool, like Wisconsin Dells, or been out in the ocean, or one of the Great Lakes where they have waves coming in, if you float out far enough away from shore, waves pass you by, but you don't move side to side with the wave, you just bob up and down. And so does the water. The water next to you isn't moving with the wave into shore, crashing onto the shore. The water next to you is just bouncing up and down, and that propagation is moving. A really wonderful example for football fans out there, or sports fans, is the wave. Right? What is the wave? It's when you stand up and throw your arms in the air, and that propagates around the stadium, hopefully, if it's a successful wave. But you don't move around the stadium. You sit in your seat. You come up and then sit back down. You have made no lateral motion in the direction of the wave. You've just oscillated locally. So the wave is the disturbance that propagates and is created by oscillations of objects, of physical media usually. For the case of light waves, it's electromagnetic waves. It's an electric field that oscillates, and we'll talk about that next semester. But just to give you the distinction between simple harmonic motion and waves, waves aren't really a thing. Waves are a result of a disturbance that propagates through a medium. A wave is not a physical object. It's a transport of energy. Now the wave velocity, v subscript w, is the speed at which the wave moves. The speed of the wave is equal to its frequency times the wavelength. Now wavelength is a new concept. Frequency is the number of oscillations per second. Wavelength is how far are between the peaks, physical peaks, and the wave. So think of water waves in the ocean. The distance between the peak to the peak is the wavelength of the wave. For sound waves, it's the distance between those vibration compressions in the air. If you know what the frequency is of the wave and you know the wavelength of the wave, you can just simply multiply those two things together and you get the wave's velocity. The units work out beautifully, right? Wavelength is a distance, it's in meters. Frequency is in hertz, which is 1 over seconds. So meters times 1 over seconds is meters per second, which is a speed or velocity. Now there are two major types of waves, and they differ on how things oscillate. Longitudinal waves create oscillations in the direction the wave travels. An example of that is, imagine you're waiting to get into a Packer game. Everyone is packed in nice and tight, right? Packed in as close as you can barely move. If you shove that person forward in front of you, that wave, that you're shoving them in the direction, they will move a little bit, but then they shove into the person in front of them, who gets shoved into the person in front of them, who gets shoved into the person in front of them. So that disturbance moves forward, and everyone is moving back and forth in that direction of the wave travel. So you're moving in the horizontal direction, everyone moves a little bit in the horizontal direction, and the wave propagates in the horizontal direction. That's a longitudinal wave. An example of a longitudinal wave are sound waves. Sound waves are when air molecules smash into adjacent air molecules, which smash into adjacent air molecules, and so on, creating the compression wave or pressure wave, a longitudinal wave that propagates forward. And it propagates in water, it propagates in metal, and so on. A transverse wave is when the propagation is perpendicular to the oscillation. So the wave moves forward, but the oscillation is up and down. And the wave for the stadium is a wonderful example of this, right? You stand up in your chair and you sit back down. The person next to you does the same thing. The wave is moving to your right or to your left, but your motion is up and down. That's a transverse wave. Light is a transverse wave. Water waves are transverse waves. Now, earthquakes actually are both. For those of you who've had a geology course, earthquakes, there are two types of waves, P and S waves for earthquakes, primary and secondary waves. One of those is a transverse wave, the other is a longitudinal wave. So earthquakes actually experience, the disturbance of an earthquake actually takes the form of both types of waves. So again, a wave is a disturbance that moves through a medium. You can figure out what its velocity is using this equation, and there are two basic types of waves. We'll be looking at transverse waves when we talk about light next semester, longitudinal waves when we talk about sound and music in the next section, in the next unit.